Hello friends, welcome back to my YouTube channel. In this class I am going to discuss some PYQs of GATE which are based upon the concept of cyclic heat engine. Before starting I must say one thing to all of you, please do subscribe to this channel, of course like it and share it to your friends. Let's get started. The first question was asked in the GATE 2019 ESE and the question is like this: a reversible cyclic device absorbs 400 kilojoule per second heat from a reservoir maintained at 265 Kelvin and rejects heat to another reservoir at 298 Kelvin. The magnitude of the rate of work done in kilowatt on the device is, out of these four options, one would be the correct answer, and it was asked in the GATE 2019 ESE paper. You see, this is a work consuming device because the heat is absorbed by this particular cyclic device from a low temperature reservoir, that is TL is 265 Kelvin, and rejects heat to another reservoir which is a higher temperature TH. And obviously when a device like a refrigerator and heat pump transfers heat from low temperature to high temperature, some work is consumed. Suppose the device is a work consuming device and this is your TH, this is TL. TL is 265 Kelvin. This is given in the question. Low temperature reservoir is 265 Kelvin and high temperature reservoir is 298 Kelvin. So this is a work consuming device. Suppose this heat transfer from low temperature to this device is Q dot L. That means this device absorbs this amount of heat. Rate of heat that is absorbed by this cyclic device Q dot L, and suppose work is input to this device, that is W dot, and this is the rate of heat that is transferred to the high temperature reservoir. So magnitude of rate of work done on the device is to be calculated. Since it is a reversible cyclic device, this relationship will be valid for it, that is QH dot, thermodynamic temperature scale, QH dot divided by TH is equal to Q dot L divided by TL. By applying this relationship, QH dot I can calculate, that is Q dot L divided by TL multiplied by TH. Q dot L is given in the question, that is 400 kilojoule per second. Absorbs 400 kilojoule per second heat from a reservoir maintained at 265. This Q dot L is given. So this is equal to Q dot L is 400 kilowatt multiplied by TH divided by TL. TH is 298. So 298 divided by 265. 400 multiplied by 298 by 265, this much of kilojoule per second or kilowatt. So from this Q dot H comes out to be 449.81 kilowatt. This is Q dot H. But what is required to be found out is magnitude of the rate of work done. By applying principle of energy balance to this cyclic device, we know that total summation of energy entering into the device during this cyclic process is equal to summation of energy leaving the device. And so Q dot L plus W dot is equal to Q dot H. So W dot is equal to Q dot H minus Q dot L. So W dot, we are to find out W dot is equal to QH dot minus Q dot L. Q dot H, this is the Q dot H, that is 449.81 minus Q dot L is, this is 400 kilowatt. Kilojoule per second means kilowatt. So this is 49.81 kilowatt. 49.81 kilowatt. So option D is the correct answer. Option D, 49.81 kilowatt work is required to run this cyclic device. Next question is, a Carnot engine receives 2000 kilojoule heat from a source at 1200 Kelvin and rejects 500 kilojoule heat to a sink. The sink temperature in Kelvin is how much? It was asked in the GATE 2019 ESE. You see, a Carnot engine receives 2000 kilojoule heat from a source. Obviously, engine means it transfers, always work will be produced by a heat engine, and it is a work producing device. So this is suppose TH, high temperature reservoir. This is source 1200 Kelvin and rejects to sink. The sink temperature is what you are required to find out. So you see, this is a heat engine, clockwise device, heat engine. It receives 2000 kilojoule heat from a source. Q dot H, it is actually in fact expressed in terms of energy, not in terms of power. So that's why this is QH, not Q dot H. QH is 2000 kilojoule and rejects 500 kilojoule heat to sink. Rejects 500 kilojoule to sink. So this heat is QL is 500 kilojoule. So what is required to be found out is TL. You see, for a reversible engine or Carnot engine, we know that this relationship is applicable, that is QH according to thermodynamic temperature scale, QH upon TH is equal to QL upon TL. This relationship is valid only for a reversible cycle or when for any device which operates on reversible cycle. So QH upon TH is equal to QL upon TL. 2000 divided by 1200, this is in terms of kilojoule, this is Kelvin, is equal to 500 divided by TL. From this, if this is equal to this, from that TL can be easily calculated. TL will be 1200 multiplied by 500 divided by 2000. So this is 300 Kelvin. So answer will be, the sink temperature will be 300 Kelvin. So this is in Kelvin, the sink temperature in Kelvin will be 300. 300 would be the answer. So question number 3. You see, the question is like this, and this was asked in the GATE 2019 ESE. GATE 2019 ESE. The question is like this: a Carnot cycle implemented using an ideal gas in a piston cylinder system will have, these 4 statements are given: work transfer in 2 parts of the cycle and heat transfer in other 2 parts of the cycle. Work transfer in all 4 parts of the cycle and heat transfer in 2 parts of the cycle. Then statement C is work transfer in 2 parts of the cycle and heat transfer in all 4 parts of the cycle. Work transfer in Option statement D is work transfer in all four parts of the cycle and heat transfer in all four parts of the cycle. You see, Carnot cycle consists of four processes, two reversible isothermal and two, suppose this is the PV diagram. This is first process in Carnot cycle is reversible isothermal, and this is second process is reversible adiabatic, then second process is obviously same reversible isothermal, and this one is reversible adiabatic process. You see, in case of adiabatic process, there is no heat transfer. Adiabatic process is a process in which there is no heat transfer. Of course, work interaction is there. And in case of isothermal process, both heat transfer and work transfer are there. So, out of the given statements, only the option B is the correct answer, because that states that work transfer in all four parts of the cycle. There is no problem in that. Every process, in all the four processes, there will be some work interactions. But in these two reversible adiabatic processes, there will be no heat transfer, because according to the definition of adiabatic process, it is a process in which there is no heat transfer. So heat transfer is there only in these two isothermal processes, but work transfer is there in all the four processes of the cycle. So that's why from the given statement you see the option B states that work transfer in all four parts of the cycle and heat transfer in work transfer in work transfer in all four parts of the cycle and heat transfer in two parts of the cycle. So this statement is correct one. All other statements are wrong. You see, option C is work transfer in two parts of the cycle and heat transfer in all four parts of the cycle. This is not correct. So only the correct option is work transfer in all. There is possibility, there is actually work interaction in all the four processes. Adiabatic process में भी work होता है, but heat transfer is not there in case of adiabatic processes. And out of these four processes, two are adiabatic and two are isothermal. So of all the four processes, you will find work interactions, but only in case of two processes you will find heat interactions. So option B will be the correct answer. So next question is question number 4, which was asked in GATE 2016 XC. GATE 2016 XC. So question is like this: consider the following statements related to the second law of thermodynamics. First statement is a cyclic heat engine cannot produce net work by exchanging heat with only one reservoir. And second statement is the efficiency of a reversible heat engine is dependent on the nature and amount of working substance undergoing the cycle. And the statement R is it is impossible to have a cyclic device which will produce no effect other than the transfer of heat from a cold body to hot body. Then statement S is it is impossible to have heat engines operating between a heat source and the sink to have a lower efficiency than that of reversible heat engine operating between the same source and sink. For which of the following options both these statements are inconsistent with the second law of thermodynamics? You see, out of the four given statements, which statements are consistent with, first we will find out which statements are consistent with the second law of thermodynamics. and we have to find out which statements are inconsistent. Sometimes students commit mistake by finding out the statements which are consistent with second law, and those statements become their correct options, but that is wrong, because the question it is written that you have to find out the statements which are inconsistent. That means those are not in agreement with the second law of thermodynamics. So you see, first statement, we will go through each statement. A cyclic heat engine cannot produce net work by exchanging heat only with one reservoir. That is what the Kelvin-Planck statement of second law states. This is Kelvin-Planck statement. This is nothing but Kelvin-Planck statement. So that means this is in consistence with the second law of thermodynamics. Kelvin-Planck statement is one of the second law statements. So this is in conformity, or this is in consistence with the second law of thermodynamics. So this is not inconsistent, but we are required to find out the inconsistent statement. And option Q, the efficiency of a reversible heat engine is dependent on the nature and amount of working substance undergoing the cycle. This is actually inconsistent. You see, this is actually inconsistent, because we know, according to the corollary of Carnot, or you can say according to Carnot principle, in fact it is the Carnot theorem actually, the efficiency of a reversible heat engine is independent of the nature or amount of working substance undergoing the cycle, because the efficiency only depends upon the temperature, source temperature and sink temperature. It doesn't depend upon the nature or amount of working substance which undergo the cycle. That's what one of the Carnot corollary states. So this is inconsistent. Then it is impossible to have a cyclic device which will produce no effect other than the transfer of heat from a cold body to hot body. So this is what the Clausius statement says. This is what the Clausius statement of second law of thermodynamics states. So that means this is again inconsistent with the second law of thermodynamics. This is consistent. This is not inconsistent with the second law of thermodynamics. And statement S, it is impossible to have heat engines operating between a heat source and the sink to have a lower efficiency than that of a reversible heat engine operating between the same source and the sink. This is actually a wrong statement. This is inconsistent, because according to Carnot theorem, it is impossible, actually no heat engine, actually the efficiency of a reversible heat engine is the maximum efficiency possible between two given temperatures. Except this reversible heat engine, whatever heat engines will be there, its efficiency will be less than that of the reversible heat engine. So there is nothing wrong with this statement. This statement is completely false. This is not correct statement. So it is possible. It is actually, if it had been possible, then this statement would have been correct. So this is inconsistent. So S is inconsistent and Q is inconsistent with the second law of thermodynamics. So we have to find out which statements are inconsistent. So obviously our answer will be the option D. Q and S statements are inconsistent. These two statements are inconsistent with second law of thermodynamics. So Q and S. So next question is question number 5. A cycle 1, 2, 3 is proposed with the following process. 1, 2, a constant pressure process, constant pressure expansion. 2, 3, reversible adiabatic expansion. 2, 3, reversible adiabatic expansion. 3, 1, irreversible adiabatic compression. Which one of the following statements is true? The net work of the cycle is 0 because there is no heat transfer. The cycle is feasible and can deliver net positive work. The cycle is impossible according to Kelvin-Planck statement. The cycle is impossible in accordance with the first law of thermodynamics. This was asked in the GATE 2015 XC. You see, The cycle can be drawn on PV diagram like this. First process is constant pressure expansion. Constant pressure expansion. Then second 2 3 this process 1 2 is constant pressure expansion. Then 2 3 is reversible adiabatic expansion. Reversible adiabatic expansion. Reversible adiabatic expansion. But the 3 1 is irreversible adiabatic compression. So obviously the process can be like this. This is an irreversible process. So it has to be a dotted line rather than a full line, because irreversible processes are always indicated by dotted lines, and the full lines always represent the reversible process. So you see, only heat interaction takes place here, because this is a constant pressure process. Some work is done, and obviously since expansion takes place means heat is transferred to the system during this process, but there is no heat interactions during these two processes. No heat interactions in these two processes, because these two are adiabatic processes. This 2 3 is reversible adiabatic process, and 3 1 is irreversible adiabatic compression. This one is expansion obviously. So there is no heat interaction. So according to Kelvin Planck statement, no work transfer or no device can operate in cyclic manner and produces some network output by exchanging heat only with one reservoir. In this case, obviously some area will be there, work will be produced, but this is not feasible, because this is violative of second law of thermodynamics. How can a device produce work in a cycle by exchanging heat with only one reservoir? Here only one heat interaction takes place during these two processes, and some network output is produced, because included area in PV diagram represents network output. But this is violative of Kelvin Planck statement of second law of thermodynamics, because this cyclic device exchanges heat with only one reservoir during the process 1 2, and in not two other processes 2 3 and 3 1, because they are adiabatic processes. So the correct option will be, the cycle is impossible. The cycle is impossible according to the Kelvin Planck statement. So option C would be correct answer. Option C would be correct answer. So this question number 6, it was asked in GATE 2015 chemistry. So you see, first question, this question number 6 is like this. For the above Carnot cycle undergone by an ideal gas, identify the process in which the change in internal energy is non-zero. You know, Carnot cycle consists of 4 processes, out of which 2 are isothermal and 2 are adiabatic. And if the working fluid is an ideal gas, you know, for ideal gas, internal energy, internal energy U is function of temperature only. For ideal gas, according to Joule's law, for an ideal gas, this internal energy U is only a function of temperature only. You know, for these two isothermal processes, I and 3I, internal energy is constant, because in case of isothermal processes there is no change in temperature during the process. Only temperature remains constant during the process. That's why the processes are called isothermal processes. So during the processes I and 3I, change in internal energy will be 0. Delta U, that is change in internal energy, will be 0 for process I and 3I. Since these two processes in this diagram you see, this process I and 3I are isothermal processes. So change in internal energy will be 0 for these two processes. For the rest of the processes, they will not be 0. They will be non-zero. They will be non-zero. That means for 2I and IB, the second and fourth process, which are adiabatic processes, for those processes temperature is not constant, so that's why internal energy will change. So in this case adiabatic expansion, there will be decrease in internal energy, and in this case in the fourth process there will be increase in internal energy. So there will change in internal energy is non-zero for processes 2I and IB. Those are adiabatic. For isothermal processes, always change in internal energy is zero or internal energy remains constant, especially for an ideal gas. Ideal gas. So the correct option would be the option B. 2I and IB are the processes in which the change in internal energy is non-zero. That's all. Thanks for watching.